Let's start our discussion of electric potential by looking at a situation where we have two plates parallel to each other. You have positive charge on one plate, negative charge on the other, and you have an electric field in between both plates. So what would happen if I were to put a positive charge next to this plate? I got the wrong color here. Put a positive charge here next to the positive plate. Well, at this point you have the forces wanting to repel this charge away, and you have the negative charge wanting to attract. So at this point you have a high potential to move. Now, once the charge gets to the negative side, the negative plate, well, it's further away from the positive charges and it's closer to the negative charges where it wants to be. So you have a low potential to move. So the positive charge always moves in the direction of the electric field. So a positive charge moves in the direction of the electric field. Now let's change and let's look at a negative charge. So we'll put a negative charge here on the negative plate, and at this point the negative charge has a high potential to move. It really wants to get away from it, and when I get to the positive side I'm going to have a low potential to move. So a negative charge moves in the direction against the electric field. Now, because the electric field starts on charges and ends on charges, it's very similar to gravity. So the electric field is similar to gravity. Even the formulas, Coulomb's law and Newton's law of gravity, are very close to each other in form. And so that means that, as we found with gravity, the electric field is conservative, meaning that it requires the same amount of work to go from point A to point B, independent of the path. And that's what we found with gravity. So work is just equal to the difference in the kinetic energy. And the difference in kinetic energy is just equal to the force on the mass through a distance. And for a particle, the force is just the mass times the acceleration times the distance. And in formula of mass and velocity, it's 1/2 mass times velocity at b squared minus 1/2 mass velocity at point A squared. But in the electrical sense, that's just the charge moving through an electrical field a certain distance. Now the difference in potential energy is just equal to the negative of the work. And that's just going to be negative of the force times the distance, negative of the mass times the acceleration times the distance, and in the electrical sense, negative of the Q times the electric field times the distance. Now remember, potential is a scalar. Not a vector. For electric potential, it's defined as the stored energy per unit charge. So we can define potential, we use the letter V at some point, is equal to the potential energy at that point divided by the value of the charge. And if we have the potential BA, that's just equal to VB, potential at point B, minus the potential at point A. And using this definition above, that just gives us the energy, potential energy at point B, minus the potential energy at point A, divided by Q, and that's just equal to the negative of the work, BA, over Q. So we have a lot of expressions that we can use that all add up, that are all equal. UB minus UA is equal to negative of the work from B to A is equal to the charge times the potential difference between A and B, and that's just equal to Q times the potential at B minus the potential at A. That's just equal to minus Q times the electric field times the distance the charge moves through, and that's just equal to minus force times distance, and equal to minus mass times acceleration times distance. All of these all are equal.